Next one is general form of LC oscillators. So LC oscillators will always consist of a tank circuit. So tank circuit, it is L parallel to C, and mostly LC oscillators are used at high frequency operation. So whenever you want to generate sine wave at very high frequency, we'll go for LC oscillators. And we will be studying three types of LC oscillators: Hartley, Colpitts, and Clap. So they all have a similar pattern of design. So we'll generally see what is the general form of LC oscillators, and then we'll try to fit in what components will be available for Hartley, Colpitts, and Clap. So I'm going to have an amplifier, and in the feedback path, I'm going to have a reactance-based feedback loop. So I'm going to have an Z1, Z2, Z3. I'm going to have a three reactance-based system which are going to act like the feedback network. And I'm going to have an amplifier. So the output of amplifier is given to this feedback component. Again, the output of feedback is again fed back to the input to your amplifier. The amplifier, what you consider, can be a BJT, it can be a FET, it can be an op amp, it can be anything. The amplifier, it can be whatever amplifier which you can use it for generating oscillations. So here we are going to see transistorized oscillators. So we will be using mostly BJT, common emitter amplifier. So the notations you see here, the input of the amplifier is 1, output is taken from port 2, and common emitter, so port 3 is grounded. And Z1, Z2, Z3 are reactive elements which are present in the feedback path of your amplifier. And the midpoint of Z1 and Z2 is grounded, and Z3 is connected across Z1, Z2 combination. Now I am replacing the transistor by H parameter model. So I will have HIE input impedance and HFE IB. I am neglecting all the other I'm using the approximate H parameter model. I'm neglecting all the other unnecessary components which are present in the H parameter model. I'm going to keep it as simple as possible. And the input current is going to be IB, the output current is going to be IC, and the current flowing through here, it is I1. And here I'm going to assume the current flowing through Z2 is I2. So these are the notations I'm using it for the LC oscillators. So Z1, Z2, Z3 are reactive elements. See, I am going to use reactive elements. I am not going to use resistive element because resistance will not contribute to any phase shift. The amplifier will have a phase shift of 180 degrees. So the remaining 180 degrees should come from this reactive elements only. So if I put a resistance here, then it is not going to offer any phase shift. So the phase shift is going to be 0. But I want one more 180 degree to make my phase shift 360 degrees, right? So I'm specifically going for reactive elements and not at all choosing resistive elements. Also, resistive elements will result in power dissipation, which is again going to be a drawback for me. So I'm going to go for three reactive elements, Z1, Z2, and Z3, which are a part of the tank circuit or the tuned circuit, which determine the frequency of oscillation. Z1, Z2 serve as an voltage divider, and the voltage which is coming from the port number 2 will be split, and it will be sent as input to the amplifier at port number 1. So you can see Z1, Z2 as a voltage divider network, which is going to take the output signal, reduce it, and give a portion of output signal to the input of amplifier through the base. Okay. So the voltage across Z1 is going to be the feedback signal. So generally the frequency of oscillation, it is given by this. So we will be deriving the frequency of oscillation. This generally, whenever you have an LC network, this is the frequency of oscillation, F naught equal to 1 by 2 pi root of LC. So Z1, Z2, Z3 can be inductive or capacitive. So we are going to choose whether Z1, Z2, Z3 is going to be inductive